Welcome to Sleepy Science. Tonight we gently drift into the quiet mystery of space, a place that feels endless and calm. If you enjoy this journey, consider subscribing and let me know where you are listening from. Now slowly relax as we begin. When we talk about how cold space is, we first need to understand what temperature actually means. Because temperature is not just a number, it is a measure of how much energy tiny particles carry inside them. Every atom and molecule is always moving, even in the calmest environments. And the faster they move, the warmer something feels, while slower movement means colder conditions. This idea is simple on Earth, where air, water, and solid objects constantly exchange energy. But space is very different, because space is mostly empty. There are very few particles compared to Earth. In fact, what we call empty space still contains some atoms, but they are incredibly spread out. Imagine a single grain of sand floating in a huge stadium. That is similar to how matter exists in many regions of space. Because of this, measuring temperature becomes more complex than simply placing a thermometer. On Earth, when you touch something cold, your body is losing heat to that object. And when you touch something warm, your body gains heat from it. This exchange happens through contact, through air, through liquids, through constant interaction between particles. But in space, there is almost nothing to touch, nothing to carry heat in the usual way. So the concept of temperature starts to feel more abstract, more distant. Instead of thinking about temperature as something you feel directly, in space it is often defined by the energy of radiation, tiny waves of energy moving through the vacuum. These waves, especially infrared radiation, carry heat without needing physical matter. So even in complete emptiness, energy still travels, silently and continuously, shaping what we describe as temperature. If you were floating far away from any star, surrounded by deep darkness, your body would slowly lose heat, not because the space around you is actively cold like ice, but because your warmth would radiate away into the vast emptiness, with nothing nearby to return that energy. It is not that space pulls heat from you, but rather that your heat simply escapes and disappears into the infinite distance. This is why space can feel colder than anything we experience on Earth, not because it is filled with freezing material, but because it lacks the ability to hold or return heat. It is a place where energy drifts away endlessly, where warmth is not shared, but lost, slowly and quietly. In many ways, calling space cold is a simplification, because cold usually means something is actively taking heat from you. But space does not behave like that. It is more like a silent void where heat fades away, like a whisper that never echoes back. And this difference is important, because it changes how we imagine the environment beyond our planet. As you continue to relax and drift deeper into this calm understanding, imagine the vastness around you, not as a freezing storm, but as a peaceful emptiness, where energy moves gently and slowly, where temperature is not something you feel instantly, but something that reveals itself over time, through the quiet loss of warmth, into the endless night. As we continue drifting through this quiet journey, the idea of temperature becomes softer and more distant, because in space, there is no air to carry warmth, no surface to easily compare, and no simple way to say something feels hot or cold. Instead, scientists must rely on careful observation, subtle signals, and instruments designed to read the faint traces of energy moving through the darkness. On Earth, a thermometer works because particles around it are constantly colliding with its surface, transferring energy, allowing it to reach the same temperature as its surroundings. But in space, where particles are extremely rare, this process does not happen in the same way. A thermometer placed in open space would not quickly adjust. It would instead be influenced mainly by radiation, by the invisible light coming from stars, planets, and distant cosmic sources. This is why measuring temperature in space is less about touching and more about observing energy, Scientists look at infrared radiation, a type of light that carries heat, even though it cannot be seen by human eyes. Every object that has any temperature at all emits this radiation, and by detecting its intensity and pattern, scientists can estimate how warm or cold something is, even from vast distances. Telescopes designed for this purpose are extremely sensitive. They can detect faint heat signals from objects billions of kilometers away. They do not rely on contact, but on light, on the gentle flow of energy that travels endlessly through the vacuum. Instruments on board satellites and probes measure this radiation carefully, converting it into data that reveals temperature in places where no human could ever reach directly. Another important method involves studying the motion of particles. Even though space is mostly empty, there are still clouds of gas and dust, especially between stars. By analyzing how fast these particles move, scientists can estimate their temperature. Faster motion indicates higher energy. Slower motion suggests colder conditions. This method connects back to the fundamental idea that temperature is simply energy in motion. Sometimes temperature is also inferred by observing how materials behave. For example, how certain gases emit light at specific wavelengths depending on their energy state. These patterns act like fingerprints, revealing the conditions in distant regions of space, allowing scientists to map temperatures across galaxies, nebulae, and even the space between galaxies. What makes this process so fascinating is how indirect it is. Nothing is measured by touch, nothing is immediate. Everything is interpreted through signals, through light, through motion, through patterns that require patience and understanding to decode. It is a quiet science, one that listens rather than feels. As you imagine this, picture instruments floating silently in orbit, gently collecting faint whispers of energy from the universe, turning invisible radiation into knowledge, revealing temperatures in places that are otherwise unreachable. It is a calm and careful process, one that mirrors the stillness of space itself. And as your mind slows down with this idea, you begin to understand that in space, temperature is not something you simply experience. It is something you discover, something hidden within light and motion, waiting to be gently uncovered across the vast and peaceful darkness. As we continue drifting deeper into this calm and quiet understanding, we arrive at a question that feels simple at first, yet becomes more mysterious the longer we think about it. What is the actual temperature of space? Not in one place, not near a star or a planet, but the average temperature of the universe itself. When scientists try to answer this, they are not looking at a single location, but at the vast emptiness between galaxies, far away from stars, far away from any strong sources of energy. In these deep regions, where almost nothing exists, a quiet baseline temperature appears, a gentle background warmth that fills the universe almost evenly. This temperature is incredibly low, about -270 degrees Celsius, which is just a few degrees above absolute zero, the coldest possible temperature where all motion nearly stops. This number may sound extreme, but in the emptiness of space, it represents a kind of balance, a soft and steady energy that remains even when everything else is far away. This faint warmth comes from a phenomenon known as the cosmic microwave background radiation, a subtle glow that fills the entire universe. It is not visible to the human eye, but it exists everywhere, surrounding every galaxy, every star, and every empty region in between, like a quiet echo of the universe's earliest moments. Long ago, the universe was extremely hot and dense, filled with energy and light, but as it expanded, it cooled down, and this ancient light stretched, becoming weaker and colder over time. Today it remains as a faint microwave radiation, carrying with it a temperature of about 2.7 degrees above absolute zero, a gentle reminder of the universe's beginning. What makes this even more calming to imagine is how uniform this temperature is. No matter where you go in deep space, far from stars and galaxies, you would find this same soft background warmth. It does not fluctuate wildly. It does not disappear. It is always there, like a quiet presence that never leaves. Like a quiet presence that never leaves. However, this does not mean all of space shares the same temperature. Near stars like our sun, temperatures can rise dramatically, while in shadowed regions or deep intergalactic space, it can feel even colder. But when we speak of the average, we are speaking of this peaceful baseline, this universal whisper of warmth that fills the void. If you were floating far away from any star, surrounded only by darkness, your body would slowly cool, radiating heat away, until it reached a balance with this background temperature, not instantly, but gradually, gently, over time, until you became part of that quiet equilibrium. As you relax further into this idea, imagine the universe not as a chaotic place, but as something softly balanced, where even in the deepest emptiness, there is still a trace of warmth, a faint glow that connects everything, stretching across unimaginable distances, holding the universe together in a calm and silent harmony. As we continue drifting gently through this vast and silent universe, we begin to focus more closely on that faint warmth we discovered, the soft energy that exists even in the deepest emptiness. This subtle presence is not just a background detail. It is one of the most important clues we have about the nature of the universe itself. This gentle glow, known as the cosmic microwave background radiation, is not something you can see with your eyes. It does not shine like a star or glow like a planet. Instead, it exists quietly, filling every direction, every corner of space, like a calm and invisible ocean of energy. What makes this radiation so fascinating is that it comes from a time long before stars existed, from a period when the universe was still young, dense, and filled with light. As the universe expanded, that light stretched, its energy slowly decreasing, its temperature gradually cooling until it became the faint microwave signal we detect today. If we had special eyes that could see this radiation, the entire sky would appear softly illuminated, not bright or overwhelming, but gently glowing in every direction, with almost perfect uniformity. No matter where you looked, you would see the same calm pattern, the same quiet presence surrounding you. Scientists have studied this glow in incredible detail, mapping tiny variations in its temperature. Differences so small, they are almost impossible to imagine. These slight changes reveal the early structure of the universe, showing where matter would eventually gather, where galaxies would form, where stars would ignite. It is like looking at the universe's memory, preserved in a soft and ancient light. What is especially peaceful about this idea is how constant it is. No matter where you travel, no matter how far you go, this background radiation remains. It does not fade away completely. It does not disappear. It continues to exist as a steady, gentle signal, connecting all of space with a shared history. And even though its temperature is extremely low, just a few degrees above absolute zero, it is still there, quietly influencing everything, setting the baseline for the coldness of space, reminding us that even in the emptiest regions, there is still something present, something subtle and enduring. As you let this thought settle, imagine floating in a place where darkness is not truly empty, where every direction holds a faint trace of ancient light, where the universe softly glows with the memory of its beginning, not loudly, not brightly, but in a calm and peaceful way that never disturbs the silence. And in that stillness, you begin to feel that space is not simply cold and empty, but quietly filled with something gentle, something ancient, something that has been traveling for billions of years, surrounding everything without ever asking to be seen. As we continue this slow and peaceful journey, we arrive at one of the most fundamental ideas in understanding cold, a concept that feels both simple and deeply mysterious: the idea of absolute zero, the lowest possible temperature that can exist in the universe. Absolute zero is defined as -273 degrees Celsius, or 0 Kelvin. At this point, the motion of particles becomes as slow as physically possible, not completely stopped, but reduced to the smallest movement allowed by the laws of nature. It is a state where energy is nearly absent, where activity fades into stillness. This idea helps us understand just how cold space can truly become, because while the average temperature of the universe is slightly above this limit, around 2.7 Kelvin, it is still incredibly close to absolute zero, meaning that most of space exists in a condition that is almost as cold as physically possible. But reaching absolute zero exactly is something that cannot happen naturally, and even in the emptiest regions of space, there is always a tiny amount of energy present, whether from the faint cosmic background radiation, or from distant stars, or from subtle interactions between particles. There is always something preventing total stillness. What makes this even more interesting is how different this kind of cold is compared to what we experience on Earth. When we think of something extremely cold, we imagine ice, frost, or freezing wind. But those are environments filled with matter, filled with particles actively taking heat away from us. In space, the cold is not aggressive. It is not forceful. It is simply the absence of energy. If you were placed in deep space far from any star, your body would not instantly freeze solid. Instead, it would slowly lose heat through radiation, gradually approaching the surrounding temperature. This process would feel quiet and slow, not sudden or violent, because there is no medium to rapidly pull heat away. This creates a strange and calming picture of cold, one where nothing rushes, nothing attacks, where temperature changes happen over time, gently and continuously, like a slow fading of warmth rather than a sharp drop. Scientists on Earth have tried to reach temperatures close to absolute zero in laboratories, using advanced techniques to remove as much energy as possible from particles. And even then, they can only approach it, never fully reach it. This shows how extreme and rare such conditions are, even compared to the already cold vastness of space. As you let your thoughts drift further, imagine a place where motion nearly disappears, where energy becomes almost still, where everything slows to its quietest state. This is the edge of cold, not dramatic, not chaotic, but calm, silent, and incredibly gentle, a kind of stillness that exists at the very limits of the universe. As we continue floating gently through this vast and quiet universe, we begin to approach regions where light becomes stronger, where a nearby star begins to dominate the environment, and where the idea of cold space starts to shift, not because space itself becomes filled with warmth, but because energy from a star changes how objects experience temperature. Near a star like the Sun, the surrounding space is still mostly empty, still lacking air, still unable to hold heat in the way we are familiar with on Earth. Yet the radiation coming from the star is intense, constant, and powerful, carrying energy across millions of kilometers, reaching anything exposed to it. If you were in open space near the Sun, something very unusual would happen. The side of your body facing the sun would begin to heat up quickly, absorbing energy from the sunlight, while the side facing away would remain extremely cold, losing heat into the darkness. This creates a dramatic contrast, where hot and cold exist at the same time, separated only by direction. This effect is very different from anything we experience on Earth, because here, air and atmosphere help distribute heat evenly, reducing extremes. But in space, there is no such balance, no medium to carry warmth from one side to another. Every surface interacts with radiation independently, creating sharp differences in temperature. Objects in orbit around the Earth experience this constantly. Satellites, space stations, and even small pieces of debris can become extremely hot when exposed to direct sunlight, reaching temperatures above 100 degrees Celsius, while at the same time, shaded areas can drop far below freezing. sometimes reaching -150 degrees Celsius or even colder. This does not mean that space itself has become hot near the sun. It remains a vacuum, still unable to store heat. What changes is the amount of energy passing through it. The intensity of radiation increases, but the environment itself does not hold that energy. It simply allows it to travel freely. This creates a kind of illusion where we might think space near the sun is warm, but in reality, it is still empty and cold. Only objects directly interacting with sunlight experience heat, while anything hidden in shadow remains in deep cold, unaffected by the nearby star. Even spacecraft must be carefully designed to handle this contrast, using reflective surfaces, insulation, and controlled orientation to manage the constant shift between heating and cooling. Without these protections, the extreme differences could damage equipment or cause systems to fail. As you relax deeper into this thought, imagine drifting near a bright star, feeling warmth only when facing the light, and a deep, quiet cold when turning away. A balance between energy and emptiness, where heat is not everywhere, but only where light chooses to touch. And in that gentle contrast, you begin to understand that space is not simply cold or hot, but something more subtle, a place where temperature depends on direction, on exposure, on the quiet dance between light and darkness across the endless void. As we continue drifting calmly through this silent expanse, we move closer to a place that feels more familiar, the region surrounding our own planet, where human technology quietly circles above the atmosphere, where objects experience a constant and gentle transition between light and shadow, between warmth and deep cold. In orbit around Earth, temperature is not stable. It does not remain fixed or predictable in the way we are used to on the surface. Instead, it changes continuously, depending on whether an object is facing the sun or hidden behind the Earth. This creates a slow rhythm, a cycle of heating and cooling that repeats over and over again. A spacecraft orbiting Earth can move from sunlight into darkness in less than an hour during the sunlit phase. Surfaces exposed to direct sunlight absorb energy and begin to warm, sometimes reaching temperatures above 100 degrees Celsius, while at the same time, shaded surfaces remain extremely cold, often far below freezing, sometimes approaching -100 degrees Celsius or lower. This constant transition creates a delicate balance, because materials expand when heated and contract when cooled, and in space, this expansion and contraction happens repeatedly, slowly, quietly, but continuously. Engineers must design spacecraft to handle this gentle stress, ensuring that structures remain stable despite these constant changes. The NASA and other organizations have studied these effects in great detail, especially through missions involving satellites and the International Space Station, where astronauts live and work in this environment. Inside the station, temperature is carefully controlled, kept comfortable and stable, but just outside its walls, the environment shifts between intense heat and deep cold. Without protection, equipment exposed to these conditions could overheat or freeze, which is why spacecraft are covered in specialized materials. Reflective coatings help reduce heat absorption, while insulation helps slow down the loss of heat into space. These systems work together quietly, maintaining balance in an environment that offers none on its own. Interestingly, even though orbit is relatively close to Earth, only a few hundred kilometers above the surface, the absence of atmosphere changes everything. There is no air to carry warmth, no wind to distribute energy, no natural system to smooth out differences. Everything depends on radiation, on exposure, on position. If you imagine yourself floating just outside a spacecraft in orbit, you would notice this contrast clearly. When facing the sun, warmth would build slowly, not instantly, but steadily, while turning away would bring a gradual cooling. a soft and silent loss of heat into the darkness. It would not feel like wind or ice, but like a gentle fading of warmth. As your thoughts settle into this steady rhythm, you begin to see orbit not as a place of extremes, but as a place of cycles, of continuous transitions between light and shadow, warmth and cold, a slow and repeating pattern that never rushes, never stops, quietly shaping everything that moves through it. As we continue drifting slowly through this calm and endless space, we begin to notice one of the most striking features of temperature beyond Earth, the sharp and quiet divide between sunlight and shadow, a boundary that is not gradual, not softened by air or atmosphere, but clear, direct, and absolute. On Earth, light and shadow blend into each other, softened by the atmosphere, scattered by air molecules, carried by winds and currents. But in space, there is no such blending, no medium to smooth the transition. When you move from sunlight into shadow, the change is immediate in terms of energy, even if the temperature of an object adjusts more slowly. In direct sunlight, energy flows continuously. Invisible waves of radiation travel from the sun and reach any exposed surface. These waves carry warmth, and when they are absorbed, the temperature of that surface begins to rise, slowly and steadily, depending on its material, its color, and its ability to reflect or absorb energy. But just a small movement into shadow removes that source completely. No sunlight, no incoming energy, only the quiet presence of deep space, and in that darkness, objects begin to lose heat, radiating their energy away, slowly cooling as their warmth escapes into the vast emptiness. This creates a unique environment where two very different thermal conditions exist side by side, separated not by distance, but by direction. A surface can be warm on one side and extremely cold on the other at the same time, without any natural process to equalize the difference. Astronauts experience this contrast directly during spacewalks. Their suits are designed to handle both extremes, reflecting excess sunlight while also retaining internal heat. Without these systems, the human body would struggle to maintain balance, not because space is actively freezing, but because it offers no protection from losing or gaining heat. Even small objects, like tools or fragments of material, follow the same pattern, turning slowly as they float, one side warming under the sun, the other cooling in shadow, a quiet rotation between energy and emptiness, a constant exchange that never fully settles. This sharp divide also shapes how spacecraft are built. Engineers carefully control how surfaces are exposed to sunlight, how heat is absorbed, stored, or reflected. Because in space, there is no forgiving environment, no natural buffer, only direct interaction with radiation, and the silent loss of energy into darkness. As you relax deeper into this image, imagine floating at the edge of light and shadow, one side gently warmed by distant sunlight, the other embraced by a deep and quiet cold, not harsh, not aggressive, but calm and steady, a perfect balance between presence and absence, where temperature is shaped not by surroundings, but by direction, by light, and by the stillness of space itself. As we continue this calm and steady journey, we now turn our attention back towards something familiar, something that quietly surrounds us every day, the atmosphere of Earth, and how it changes everything about the way temperature behaves, not only on our planet, but in contrast to the emptiness of space. On Earth, temperature feels natural, stable, and often predictable, because the atmosphere acts like a soft and invisible blanket, holding warmth close to the surface, slowing down the loss of heat, and distributing energy across the planet. Without this layer of air, the surface of Earth would experience extreme temperature changes, much like objects in space. The atmosphere works by interacting with radiation. Sunlight passes through it and warms the surface, and then the surface releases energy back in the form of infraradiation. But instead of letting all that energy escape directly into space, The atmosphere absorbs some of it and re-emits it in all directions, including back toward the surface, creating a gentle and continuous cycle of warmth. This process allows temperatures to remain within a range that supports life, smoothing out the sharp contrasts between day and night, between sunlight and shadow. It prevents the sudden and dramatic shifts that would otherwise occur if Earth were exposed directly to the vacuum of space. Without an atmosphere, a planet behaves very differently. Surfaces heat up quickly under direct sunlight, and then lose heat just as quickly when darkness arrives. There is no buffer, no storage, no redistribution of energy, only the immediate effects of radiation and the silent cooling into space. This is why the moon, which has almost no atmosphere, experiences extreme temperature differences during its day. Surfaces can become extremely hot under direct sunlight, while during its night, temperatures drop dramatically, becoming far colder than most places on Earth, all because there is nothing to hold or share the heat. The atmosphere also allows heat to move through convection, where warm air rises and cool air sinks, creating currents that spread energy across large distances. Oceans and winds carry warmth from one region to another, balancing temperatures across the planet in a way that space cannot replicate. In space, none of this exists. No air, no convection, no natural redistribution, only radiation moving silently through emptiness, and objects responding individually to whatever energy reaches them or leaves them, without any shared system to stabilize conditions. If you imagine standing on Earth, feeling the air around you, noticing how temperature changes slowly, gently, over time, and then compare that to floating in space, where temperature depends entirely on exposure to light and the gradual loss of heat, the difference becomes clear. One environment holds warmth, the other lets it drift away. As your thoughts settle into this contrast, you begin to feel the quiet importance of the atmosphere, not as something loud or noticeable, but as a calm and protective presence, shaping every temperature we experience, while beyond it, in the vast stillness of space, warmth fades gently into the endless dark. As we continue drifting slowly through this calm and silent universe, we begin to understand something deeper about the nature of space, something that quietly explains why it feels so cold, not because it is filled with freezing material, but because it lacks the ability to hold heat, to store energy, to keep warmth close the way Earth does. On our planet, heat is constantly moving, carried by air, by water, by contact between objects. When something becomes warm, that warmth spreads. It travels through the surrounding environment, slowly balancing itself, creating a shared temperature that feels stable and continuous. This is why a warm room stays warm for a while, and why heat does not disappear instantly. But in space, there is no such system, no air, no fluid, no medium to carry heat from one place to another. The vacuum does not store energy in the way matter does. It does not absorb warmth and then release it later. Instead, it simply allows energy to pass through, silently and endlessly, without holding on to it. This means that heat in space exists only within objects themselves, not in the space around them. A spacecraft, a rock, or a human body can contain energy, can become warm or cold, but the surrounding vacuum remains unchanged. It does not warm up. It does not cool down in response. It simply remains empty, unaffected, allowing energy to move freely. The only way heat travels through space is by radiation, a process where energy moves in the form of electromagnetic waves. These waves do not need particles to carry them. They move through emptiness at the speed of light, spreading outward in all directions, gradually weakening as they travel farther away from their source. Because of this, any object in space that is warmer than its surroundings will slowly lose heat by radiating energy outward, and since there is almost nothing nearby to reflect that energy back, the heat does not return. It continues traveling into the vast distance, becoming more and more spread out, more and more diluted. This is very different from what we experience on Earth. Where heat can bounce, reflect, and circulate within an environment, in space, there is no enclosure, no boundary, no containment. Energy escapes and keeps going, never returning to its source. This is why warmth fades so completely in the vacuum. Even large objects like planets and stars cannot warm the space around them in a lasting way. They emit enormous amounts of energy. But that energy does not accumulate in the vacuum. It passes through, interacting only with objects it encounters, leaving the surrounding space itself unchanged. This creates a quiet and almost poetic reality, where space is not actively cold, but passively empty, a place where heat cannot stay, where warmth cannot gather, where energy is always on a journey outward, never settling, never resting. If you imagine holding a warm object in your hand on Earth, you can feel the heat spreading into your skin, into the air, into everything around it. But in space, that same object would slowly lose its warmth without sharing it. Without affecting anything nearby, its heat would simply drift away into the infinite darkness. As your mind settles into this understanding, you begin to see that space is not a freezing force, but a quiet absence, a place where heat is not taken, but lost, gently and continuously, fading into the endless calm, leaving behind a stillness that feels both vast and deeply peaceful. As we continue drifting through this calm and endless silence, we now focus on a question that feels almost paradoxical. How can heat move in a place where there is almost nothing? How does energy travel across the vast emptiness of space when there are no particles to carry it in the way we are familiar with on Earth? On our planet, heat moves in three main ways: conduction, and radiation. Conduction happens when objects touch and transfer energy directly. Convection happens when fluids like air or water move and carry heat with them. But in space, both of these processes are almost completely absent because they require matter, and space offers almost none. This leaves only one method: radiation, a quiet and continuous process where energy travels as waves, not through contact, not through movement of particles, but through the fabric of space itself. These waves are part of the electromagnetic spectrum, the same family as visible light, but also including infrared, ultraviolet, and many other forms. Every object that has any temperature at all emits radiation. Even something that feels cold to us still releases energy, just at a lower intensity. This means that everything in space is constantly sending out these invisible waves, slowly releasing its internal energy into the surrounding emptiness. When radiation leaves an object, it does not need anything to carry it. It moves freely, spreading outward in all directions, traveling immense distances without slowing down, without being absorbed unless it encounters another object. This is how sunlight reaches Earth across millions of kilometers of empty space. At the same time, objects can also absorb radiation. When these waves reach a surface, they transfer energy into it, causing its temperature to rise. This balance between emitting and absorbing radiation determines how warm or cold something becomes in space, not the surrounding environment, but the interaction with energy itself. This creates a very gentle and gradual system. Nothing happens instantly. Heat does not rush from one place to another. Instead, it flows quietly through radiation, slowly changing the energy state of objects over time, creating a calm and continuous exchange that never stops. If you imagine a spacecraft floating far from any star, it would slowly radiate its heat away, cooling down over time, unless it receives energy from some external source. And if it moves into sunlight, it would begin to absorb energy again, warming gradually, always adjusting, always seeking a balance between incoming and outgoing radiation. This process is silent, invisible, and constant. There are no currents, no winds, no movement of air, only waves of energy traveling through the darkness, connecting distant objects in a subtle and almost peaceful way. Even your own body emits radiation right now, releasing heat into the space around you. But on Earth, that heat is quickly replaced by the surrounding air. In space, it would simply continue outward, never returning, slowly reducing your temperature until a balance is reached. As your thoughts slow down with this idea, imagine energy moving not as something fast or forceful, but as something gentle and steady, waves traveling quietly through infinite space, carrying warmth away, bringing warmth in, creating a silent rhythm that defines temperature in the most subtle way. And in that rhythm, you begin to feel that space is not empty in the way it first appears, but filled with motion, with invisible waves, with a constant and peaceful flow of energy that shapes everything without ever making a sound. As we continue drifting gently through this vast and silent environment, we now turn our attention to something more personal, something easier to imagine. What it would actually feel like for a human body to be exposed to space, not through imagination shaped by movies, but through the quiet reality of how temperature truly behaves in the vacuum. Many people imagine space as instantly freezing, as if stepping outside would turn everything to ice in a moment. But this is not how it works, because freezing on Earth often involves cold air rapidly pulling heat away from the body. In space, there is no air, no wind, no medium to quickly remove that warmth. So the process becomes slower, more gradual, more silent. If a person were suddenly exposed to space, the body would begin losing heat through radiation, just like any other object. Energy would leave the body in the form of infrared waves, spreading outward into the emptiness. But this would not feel like touching ice. It would feel like a slow fading of warmth, not immediate, not sharp, but steady. At the same time, if the body were exposed to direct sunlight, the side facing the sun would begin to absorb energy, warming up, while the side facing away would cool down. This creates a strange dual experience, where warmth and cold exist together, depending on orientation, not on surroundings. However, temperature would not be the most immediate concern in such a situation. The absence of pressure and oxygen would affect the body much more quickly. But focusing only on temperature, the cooling process would take time, minutes rather than seconds, because radiation is not an aggressive way of removing heat. Another interesting detail is that moisture on the surface of the body would begin to evaporate rapidly in the vacuum, creating a cooling effect. But again, not an instant freezing, more like a gradual loss of heat combined with other physical changes, all happening quietly and without the familiar sensations we associate with cold environments. Spacesuits are designed to manage this delicate balance, not just to keep astronauts warm, but to regulate temperature carefully, preventing overheating when exposed to sunlight and preventing excessive cooling in shadow. Inside the suit, a controlled system circulates fluid and removes excess heat, maintaining a stable and comfortable environment. Without such protection, the human body would slowly move toward equilibrium with its surroundings, losing heat until it matched the low background temperature of space. But this would not happen instantly. It would be a gradual transition, a quiet adjustment over time. This creates a different image of cold, one that is not sharp or painful in the way we imagine, but distant and slow, a quiet loss rather than an active force, a process that unfolds gently in the absence of everything that usually surrounds us. As you settle into this thought, imagine your body not being attacked by cold, but simply releasing warmth into the vast darkness, slowly and silently, until it becomes part of the calm balance of space, where temperature is not something that strikes suddenly, but something that changes softly, almost unnoticed across time. As we continue drifting through this calm and endless silence, we now move closer to the delicate systems that allow humans to exist in space, not by changing space itself, but by creating a small, controlled environment around the body. a personal climate that gently protects against both the slow loss of heat and the sudden gain of energy from sunlight. A spacesuit is not simply a layer of insulation. It is a carefully balanced system, designed to manage temperature in a place where there is no natural stability, where warmth can build on one side and disappear on the other, where the environment offers no help in maintaining comfort, only the quiet challenge of emptiness. Inside the suit, the human body continues to produce heat, just as it does on Earth, through metabolism and movement, and this heat must be managed carefully, because in space, it cannot escape through air or convection. Without a system to remove it, the body could slowly overheat, even in the cold vacuum. To solve this, spacesuits use a network of tubes filled with liquid, often water, that flows close to the skin, absorbing excess heat and carrying it away. This liquid cooling system acts like an artificial circulation of energy, replacing the role that air and sweat would normally play on Earth. At the same time, the outer layers of the suit are designed to control how much radiation is absorbed and how much is reflected. Bright and reflective surfaces reduce the amount of solar energy entering the suit, while inner layers help retain the right amount of warmth, preventing excessive cooling when in shadow. This balance is extremely delicate because conditions in space can change constantly. A slight rotation, a small shift in position, can expose the suit to sunlight or move it into darkness. The suit must respond quietly and continuously, maintaining a stable internal temperature regardless of what happens outside. Astronauts often describe this experience as existing in two environments at once. Outside the suit, extreme differences in temperature exist side by side, while inside, everything feels controlled, calm, and consistent. A small pocket of Earth-like conditions floating in the vast emptiness. Even the visor of the helmet plays a role, filtering light, reducing heat from direct sunlight, and protecting the eyes. Every part of the suit works together, not loudly, not aggressively, but quietly and steadily, maintaining balance in a place where balance does not naturally exist. What makes this idea so peaceful to imagine is how it transforms space from something hostile into something manageable, not by changing the universe, but by gently shaping a small environment within it, creating comfort through design, through understanding, through careful control of energy. As your thoughts slow down further, imagine yourself inside such a suit, floating gently, surrounded by silence, while inside, everything remains stable, warm, and calm. A quiet contrast between the vast cold outside and the carefully maintained balance within. And in that gentle contrast, you begin to feel that even in the cold emptiness of space, warmth can exist, not as something given by the environment, but as something created, sustained, and quietly protected. As we continue this slow and peaceful journey, we now turn to the careful observations gathered over many years by those who have quietly studied space up close, not through imagination, but through instruments, missions, and long periods of silent measurement. These observations help us understand temperature not as a single number, but as a complex and shifting condition. Organizations like NASA and ESA have collected detailed data from satellites, probes, and crewed missions, revealing how temperature behaves in different parts of space, from low Earth orbit to the distant edges of the solar system. And what they show is a story not of uniform cold, but a variation shaped by light, distance, and exposure. In low Earth orbit, where spacecraft circle our planet, temperatures can change rapidly depending on position. Surfaces exposed to sunlight can heat up to over 100 degrees Celsius, while shaded areas can drop below -100 degrees Celsius. This contrast is not caused by the environment changing, but by the constant shift between radiation and shadow. Further away from Earth, as distance from the sun increases, the amount of incoming energy decreases. Spacecraft traveling toward the outer planets experience a gradual reduction in solar heating. temperatures become lower. Not because space itself changes, but because less energy is available to be absorbed. Probes sent to explore distant regions must be designed to operate in these conditions, with systems that retain heat generated internally, because far from the sun, external energy becomes too weak to maintain temperature in these regions. The cold is not aggressive, but persistent, a steady lack of incoming warmth. At the same time, missions have shown that temperature is not only about distance, but also about orientation. Even far from the sun, a surface directly facing sunlight can still absorb measurable energy, while a surface turned away remains in deep cold, reinforcing the idea that direction plays a central role in how temperature is experienced. Space agencies also measure the temperature of interplanetary space, the region between planets, and these measurements confirm that the background temperature remains extremely low, close to the faint cosmic radiation that fills the universe, a quiet baseline that exists everywhere. One of the most interesting findings is how spacecraft themselves become small sources of heat. Their electronics, systems, and operations generate energy, and without proper management, this heat can build up or escape too quickly. Engineers must carefully control both sides of this balance, ensuring stability in an unstable environment. These observations show that temperature in space is not fixed, not simple, but constantly influenced by multiple factors: light, distance, material, orientation, and internal energy, all working together quietly, shaping the conditions experienced by anything traveling through the void. As you settle deeper into this understanding, imagine countless instruments drifting through space, patiently recording these subtle changes, turning invisible energy into knowledge, revealing a universe where temperature is not defined by the environment alone, but by the delicate interaction between energy and emptiness. And in that quiet collection of data, a clearer picture forms. Space is not just cold, it is dynamic, it is responsive, it is shaped by light and motion, yet always grounded in a calm and silent background that never fades. As we continue drifting gently through this vast and quiet universe, we now begin to move across the solar system itself, exploring how temperature changes from one world to another, not because space itself becomes different, but because each planet interacts with sunlight, energy, and its own environment in a unique and quiet way. Closer to the sun, planets receive far more energy, and this directly affects their surface temperatures. For example, Mercury, the closest planet to the sun, experiences extreme conditions. During its day, its surface can become incredibly hot, reaching temperatures above 400 degrees Celsius, while during its long night, without sunlight, it cools dramatically, dropping to around -180 degrees Celsius. This large difference happens because Mercury has almost no atmosphere to hold or distribute heat. Venus, slightly farther from the sun, tells a very different story. Even though it receives less direct sunlight than Mercury, its thick atmosphere traps heat extremely effectively, creating a surface temperature of around 460 degrees Celsius almost everywhere, both day and night. This shows how powerful an atmosphere can be in holding warmth, turning a planet into a place where temperature remains stable but extremely high. Moving outward to Earth, we find a more balanced environment, where the atmosphere allows heat to circulate and moderate, keeping temperatures within a range that supports life. But beyond Earth, as we move farther from the sun, the amount of incoming energy decreases, and the average temperatures of planets begin to fall. Mars, often called the Red Planet, has a thin atmosphere, not strong enough to hold much heat. As a result, its temperatures can vary widely, from mild conditions during the day near the equator to extremely cold nights, often dropping below -100 degrees Celsius, again showing the importance of atmospheric presence. Further out, The gas giants like Jupiter and Saturn exist in regions where sunlight is much weaker. Their upper atmospheres are very cold, yet internally they generate heat, creating a complex balance between external cold and internal warmth. This adds another layer to how temperature can exist in space, not only from outside sources, but from within. Even farther away, planets like Uranus and Neptune receive very little solar energy, existing in a dim and distant region where temperatures remain extremely low. Yet even here, subtle differences appear due to internal processes and atmospheric composition, showing that temperature is never defined by a single factor. What becomes clear through this journey is that space itself does not impose a single temperature. Instead, each object, each planet, creates its own thermal identity, shaped by distance, atmosphere, composition, and energy flow, all existing within the same vast and silent environment. If you imagine traveling slowly from the inner solar system to its outer edges, you would not feel a sudden drop into cold, but a gradual fading of warmth, a steady reduction of energy, a quiet transition from bright intensity to deep stillness. As your thoughts settle into this wide perspective, you begin to see temperature not as something fixed, but as something that gently shifts across distance, shaped by each world it touches, while the space between them remains calm, empty, and quietly indifferent, allowing each planet to define its own experience of warmth and cold. As we continue drifting farther and farther from the familiar warmth of our sun, we slowly leave behind the gentle influence of its light, entering a region where stars become distant points, where their energy weakens, and where the quiet background of the universe begins to dominate. This is the space between stars, vast, calm, and deeply still. In these regions, often called interstellar space, the amount of matter becomes even smaller than before. A few atoms scattered across enormous distances, thin clouds of gas and dust drifting slowly, almost motionless. And with so little interaction, energy becomes rare, making temperature drop closer and closer to its lowest possible limit. Here, temperatures are typically just a few degrees above absolute zero, often around 10 Kelvin, or even lower in some dense regions, which is far colder than anything naturally found on Earth. Yet this cold does not feel sharp or aggressive. It is soft, distant, and incredibly stable, a quiet absence of energy rather than an active freezing force. Even though stars are scattered throughout the galaxy, their light does not significantly warm this space, because the distances are so vast that radiation spreads out and weakens long before it can have a strong effect. Each star creates a small region of influence, but beyond that, the universe returns to its calm and faint baseline. Within interstellar space, there are also large clouds known as nebulae, where gas and dust gather in slightly higher concentrations. In some of these regions, temperatures can be slightly higher due to nearby stars or internal processes, while in others, especially dense molecular clouds, temperatures can drop even further, becoming some of the coldest natural places in the galaxy. These cold clouds are not empty. They are quiet places where new stars may eventually form, where particles move slowly, gently interacting, gradually coming together over long periods of time, showing that even in extreme cold, change can still happen, just at a much slower and more peaceful pace. If you imagine yourself drifting through this interstellar darkness, you would notice how little changes around you. No strong light, no sudden heat, only distant stars and a faint background glow. Your body slowly radiating its heat away, adjusting to the stillness, becoming part of the quiet balance of the environment. The cold here is not something you would feel instantly. It would reveal itself over time, through the slow loss of energy, through the absence of warmth, through the deep and silent calm that surrounds everything. As your thoughts settle into this vast emptiness, you begin to understand that the deeper you travel into space, the more everything slows down, energy becomes rarer, motion becomes softer, and temperature approaches its lowest possible state, not dramatically, but gently, as if the universe itself is becoming quieter. And in that quiet, between the distant stars, space reveals its true nature, not as a place of harsh cold, but as a place of deep stillness, where energy fades, where movement slows, and where everything rests in a calm and endless silence. As we continue drifting even farther beyond the familiar structure of our galaxy, we now enter a scale that feels almost impossible to imagine: the space between galaxies, where distances become so vast that even light takes millions of years to travel, and where the influence of stars fades into a quiet and distant presence, leaving behind a calm and nearly uniform emptiness. This region, known as intergalactic space, is one of the coldest and most silent environments in the universe, not because it contains something that actively cools objects, but because it contains almost nothing at all. Matter becomes incredibly sparse, far more spread out than in interstellar space, sometimes reduced to just a few particles across enormous volumes, making interactions between particles extremely rare. In this deep emptiness, the temperature approaches the lowest possible limit even more closely, often hovering just slightly above the faint cosmic background radiation. Around 2 to 3 Kelvin, this is not a fluctuating or unstable temperature, but a quiet baseline, a gentle and nearly constant condition that exists across vast stretches of the universe. What makes this environment so unique is how little variation there is. Unlike regions near stars or within galaxies, where energy sources create differences in temperature, intergalactic space is almost uniform, with very few local influences, creating a sense of stillness that extends across unimaginable distances. Radiation from galaxies and stars does pass through this space, but by the time it travels such enormous distances, it becomes incredibly weak, spread thin across the vastness, contributing only a small amount of additional energy, not enough to significantly change the overall temperature. There are also traces of ionized gas in these regions, sometimes forming large-scale structures that connect galaxies, but even these structures remain extremely diffuse and cold, their particles moving slowly, carrying very little energy, existing in a state that feels almost suspended in time. If you imagine drifting through this intergalactic void, you would not see much change around you. No nearby stars, no bright sources of light, only distant galaxies appearing as faint, soft glows, and in every direction, the same quiet background, the same gentle temperature, the same deep and peaceful stillness. Your body, if unprotected, would slowly release its heat into this vast emptiness, not because anything is pulling it away, but because there is nothing to return it. The energy would simply continue outward, spreading endlessly, becoming part of the universe itself. This creates a profound sense of calm, where temperature is no longer something that changes rapidly or dramatically, but something that exists as a steady and almost unchanging presence, a quiet equilibrium that stretches across the largest scales imaginable. As your thoughts slow down with this idea, you begin to feel the true depth of space, not just as distance, but as stillness, as a place where energy is minimal, where variation is rare, where everything exists in a soft and stable balance, just above absolute zero. And in that immense quiet, between galaxies, the universe reveals its coldest and most peaceful state, not harsh, not violent, but endlessly calm, where temperature becomes almost invisible, blending into the silence of infinite space. As we continue drifting through this calm and endless universe, we now approach one of the most mysterious regions of all, a place often imagined as dark, cold, and empty, yet in reality filled with subtle and powerful contrasts. The region surrounding a black hole, where temperature behaves in ways that feel both surprising and deeply fascinating. At first, it may seem natural to think that a black hole would be extremely cold. After all, it does not emit light in the usual sense, and it appears as a dark region against the background of space. But the reality is more complex, because the space around a black hole can actually become incredibly hot, depending on what is happening nearby. When matter begins to fall toward a black hole, it does not simply disappear instantly. Instead, it forms a rotating disk around it, often called an accretion disk. Within this disk, particles move at extremely high speeds, colliding, compressing, and heating up as they spiral inward. This process can generate enormous amounts of energy, raising temperatures to millions of degrees. This means that even though the black hole itself appears dark, the region around it can glow intensely, emitting radiation across a wide range of wavelengths, from visible light to powerful X-rays, creating one of the brightest environments in the universe, not because of the black hole alone, but because of the energy released by matter falling into it. Yet just beyond this active region, space quickly returns to its usual quiet state, cold, calm, and nearly empty. This creates a sharp contrast, where extreme heat exists in a relatively small area, surrounded by vast regions of deep cold, showing once again that temperature in space is highly localized, shaped by energy sources rather than the environment itself. Interestingly, black holes are also associated with a very subtle form of temperature known as Hawking radiation, a theoretical process where black holes can emit tiny amounts of energy over extremely long periods of time. This temperature is incredibly low for large black holes, often far below the already cold background of space, making it almost impossible to detect directly. This creates a gentle paradox, where the surroundings of a black hole can be among the hottest places in the universe, while the black hole itself, in terms of this subtle radiation, can be colder than the space around it, a quiet balance between extremes that exists without conflict. If you imagine drifting near such a region, you would notice how quickly conditions change with distance. Near the accretion disk, intense light and heat, energetic and dynamic. But just a little farther away, a return to silence, to darkness, to the soft and steady cold of space. This contrast is not chaotic, not violent in the way it might seem, but structured and calm when viewed from a distance, each region existing in its own state, shaped by the flow of energy and the presence of matter, all within the same vast and quiet universe. As your thoughts settle into this image, you begin to see that even the most extreme places in space follow the same gentle rules. Temperature appears where energy gathers, and fades where energy is absent, creating a universe filled not with uniform conditions, but with quiet variations, each one existing peacefully alongside the others. And in that understanding, even a black hole, one of the most mysterious objects we know, becomes part of the same calm story, where heat and cold are not opposites in conflict, but expressions of energy, appearing and disappearing across the endless silence of space. As we continue drifting gently through the vast and quiet spaces between stars, we begin to notice that even in regions that seem completely empty, there is still something present, faint clouds of gas and dust, spread thin across enormous distances, almost invisible, yet quietly shaping the structure of the universe and carrying subtle traces of temperature within them. These clouds, often found in interstellar space, are made mostly of hydrogen, along with small amounts of other elements and tiny solid particles. And even though they are extremely diffuse compared to anything on Earth, they still contain enough matter for temperature to exist, not as something intense or dramatic, but as a gentle measure of particle motion. In many of these regions, temperatures are very low, often around 10 to 100 Kelvin. Depending on local conditions, in colder and denser clouds, especially those where stars may one day form, temperatures can drop even further, sometimes reaching just a few degrees above absolute zero, creating environments that are among the coldest natural places in the galaxy. What makes these clouds especially interesting is how slowly everything happens within them. Particles move at very low speeds, collisions are rare, and energy exchanges happen gently over long periods of time. This creates a kind of stillness where temperature remains stable and changes only gradually. Yet even in this cold and quiet environment, subtle processes continue. Radiation from distant stars can slightly warm certain regions, while denser areas can shield themselves from this energy, becoming colder and more isolated, creating small variations within the cloud. A soft pattern of temperature differences spread across space. These clouds are also important because they are the birthplaces of stars. Over time, gravity can slowly pull material together, increasing density. And as particles come closer, their motion increases, temperature begins to rise, eventually leading to the formation of new stars, showing how even in the coldest conditions, warmth can emerge over time. Dust particles within these clouds play a role as well, absorbing and emitting radiation, interacting with light in subtle ways, helping to regulate how energy moves through the cloud. Adding another layer to how temperature behaves in these regions, if you imagine drifting through such a cloud, you would not feel it in the way you feel fog or air on Earth. It would be far too thin for that, but you would be surrounded by a quiet presence. Particles scattered gently around you, moving slowly, carrying just a small amount of energy, existing in a calm and balanced state. The cold here is not empty, but filled with potential, a quiet waiting where temperature remains low, but never completely still, always holding just enough energy for change to be possible, even if that change takes millions of years to unfold. As your thoughts settle into this gentle image, you begin to see that even the coldest parts of space are not lifeless or inactive, but quietly active in their own slow way, holding the ingredients for future stars, future light, future warmth. And in that slow and peaceful process, the universe reveals a deeper truth, that cold is not the absence of possibility, but a quiet beginning, where energy rests, gathers, and waits until it slowly transforms into something new. As we continue drifting slowly through this calm and silent universe, we now begin to explore how freezing actually happens in space, not as a sudden or dramatic event, but as a quiet and gradual process shaped by the absence of air, the steady loss of energy, and the gentle balance between radiation and stillness. On Earth, freezing usually feels immediate and active. Cold air surrounds an object, pulling heat away through contact and movement. Wind increases this effect, accelerating the loss of warmth. And within a short time, temperatures drop enough for liquids to turn into solids, creating ice, frost, and familiar signs of cold. But in space, the process is very different. There is no air to surround an object, no wind to carry heat away, no medium to speed up the transfer of energy. Instead, freezing happens through radiation, the slow emission of energy into the vast emptiness, where heat simply drifts away without resistance. If a liquid were exposed to space, something interesting would happen. Rather than freezing instantly, it would begin to boil first because the pressure is so low. Molecules can escape easily, turning into vapor even at low temperatures. This rapid evaporation would remove energy from the remaining liquid, causing it to cool down. As this process continues, the temperature would drop further, and eventually, the remaining liquid would begin to freeze, forming solid structures, not because something cold is surrounding it, but because it has lost enough energy through both evaporation and radiation. This creates a unique path to freezing that feels almost reversed compared to what we expect. This means that freezing in space is not an aggressive force, not something that attacks instantly, but a quiet transformation, where energy leaves gradually, and the material slowly settles into a lower energy state. becoming solid over time. Even solid objects behave in a similar way. They do not instantly become extremely cold. Instead, they cool slowly, radiating their internal energy outward, their temperature decreasing step by step until they reach a balance with their surroundings. The speed of this process depends on many factors: the size of the object, its material, its exposure to radiation, and whether it is in sunlight or shadow. Larger objects can retain heat longer, while smaller ones lose it more quickly. But in all cases, the process remains gradual, calm, and continuous. If you imagine a small droplet of water floating in space, you would see it shimmer briefly as it begins to evaporate, then slowly cool, and eventually freeze into a delicate structure, suspended in the vacuum, not violently transformed, but gently changed over time. This creates a different image of freezing, one that is not harsh or immediate, but soft and quiet, shaped by the absence of everything that normally surrounds us, a process that unfolds slowly, almost peacefully, as energy fades away. As your thoughts settle into this idea, you begin to feel that even something as simple as freezing becomes more subtle in space, not a sudden event, but a gradual transition, a slow movement toward stillness, where temperature decreases gently and matter quietly changes form in the endless silence of the universe. As we continue drifting deeper into this vast and quiet universe, we begin to notice something that feels almost poetic, a connection between silence and temperature, not because sound directly changes how warm or cold something is, but because both silence and cold emerge from the same underlying reality: the absence of a medium, the absence of particles, the absence of interaction. On Earth, sound is everywhere. It travels through air, through water, through solid objects. Vibrations move from one particle to another, carrying energy across space. And in a similar way, heat also moves through these particles, spreading through conduction and convection, creating a world that feels alive, dynamic, and constantly in motion, where both sound and warmth are shared experiences. But in space, this shared system disappears. There is no air to carry sound, no fluid to distribute energy, no medium that connects one place to another in a continuous way. And because of this, both sound and heat behave very differently. They no longer travel through matter in the ways we are used to. They become isolated, subtle, and slow. The silence of space is not just the absence of sound. It is a reflection of emptiness itself, without particles to vibrate. There is nothing to carry sound waves. And in the same way, without particles to interact, heat cannot spread through contact or flow. It can only move through radiation, quietly and independently of everything else. This creates a unique environment where both silence and cold are deeply connected, not as direct causes of each other, but as parallel results of the same condition: the lack of matter, the vast separation between particles, the quiet stillness of the vacuum. If you imagine yourself floating in this environment, you would notice how different everything feels compared to Earth. No sound reaching your ears, no wind, no subtle background noise, only complete silence, and at the same time, no immediate sensation of temperature changing rapidly, no cold air touching your skin, only a slow and gradual loss of heat, almost unnoticeable at first. This combination creates a sense of calm that is difficult to experience anywhere else, where both sound and heat exist in their most subtle forms, where everything unfolds slowly, gently, and continuously. Even large cosmic events, explosions, collisions, powerful releases of energy happen in this silence, their effects visible through light and radiation, but never heard, and their heat spreading only through radiation, never through waves of air or pressure, reinforcing the idea that space is a place where interaction is minimal and movement is quiet. This does not mean that space lacks energy or activity, but rather that it expresses these things in a different way, without sound, without direct contact. Without the immediate sensations we are familiar with, everything becomes more distant, more gradual, more peaceful. As your thoughts continue to slow down, you begin to feel how silence and cold are not empty in a negative sense, but full of calm, full of space, full of openness, allowing everything to exist without disturbance, without noise, without urgency. And in that quiet connection, between the absence of sound and the slow fading of warmth, the universe reveals a deeper kind of stillness, one where temperature changes gently, where energy moves silently, and where everything rests in a calm and endless balance that stretches across the infinite darkness. As we continue drifting calmly through this vast and silent universe, we now begin to focus on the quiet engineering that allows human technology to exist in such an environment, not by changing space itself, but by carefully managing energy, guiding heat, and maintaining balance within machines that travel through both intense sunlight and deep shadow. A spacecraft does not simply float through a neutral environment. It moves through constant contrasts. One side may be facing direct sunlight, slowly absorbing energy, while another side remains in shadow, steadily losing heat. This creates a continuous challenge, not a sudden one, but a slow and persistent need to control temperature over time. Inside a spacecraft, electronics generate heat as they operate. Computers, instruments, communication systems all produce energy that must be managed carefully, because in space, that heat cannot escape through air. It cannot be carried away by wind or convection. It must be guided, directed, and released in a controlled way. To handle this, spacecraft use thermal control systems, quiet and carefully designed networks that move heat from where it is produced to where it can be safely released, often through special panels called radiators. These radiators do not cool by interacting with air, but by emitting infrared radiation, slowly sending excess heat into space. At the same time, spacecraft must protect themselves from losing too much heat, especially in regions far from the sun, where incoming energy is weak. Insulation layers are used to slow down the escape of warmth, trapping just enough energy inside to keep systems functioning properly, creating a delicate balance between retaining heat and releasing it. Materials play a crucial role in this process. Reflective surfaces reduce the amount of sunlight absorbed, while darker materials can be used where heat absorption is needed. Every surface is chosen carefully, every layer designed with purpose, not randomly, but with a quiet understanding of how energy behaves in the vacuum. Orientation also becomes important. Spacecraft can adjust their position relative to the sun, turning certain surfaces toward or away from light, controlling how much energy they receive. This is not done quickly or dramatically, but slowly and precisely, maintaining stability over long periods of time. Even small changes can have significant effects. A slight increase in absorbed radiation can gradually raise temperature, while extended time in shadow can slowly reduce it. So systems must constantly monitor and adjust, not reacting suddenly, but maintaining a steady equilibrium. If you imagine being inside such a spacecraft, you would not feel the extremes outside. Inside, everything remains controlled, stable, calm. Temperature stays within a comfortable range, while just beyond the walls, space continues its quiet contrast between light and darkness, warmth and cold. This creates a peaceful image of coexistence, where human technology adapts to the universe rather than fighting it, using knowledge, design, and patience to maintain balance in an environment that offers none naturally. As your thoughts settle into this idea, you begin to see that survival in space is not about resisting the cold, but about understanding energy, guiding it gently, allowing warmth to remain where it is needed, and letting excess heat drift away into the silent and endless night. And in that careful balance, spacecraft become small islands of stability, floating quietly through a universe that remains vast, cold, and calm, yet always shaped by the subtle flow of energy. As we continue drifting gently through this calm and endless universe, we now move closer to the human experience once again, not imagined from afar, but lived quietly by those who have spent time beyond Earth, where temperature is no longer something constant and familiar, but something subtle, controlled, and always present in the background. Astronauts who travel into orbit do not feel space directly. They exist inside carefully designed environments, inside spacecraft and stations where temperature is maintained with precision, kept stable and comfortable, often similar to conditions on Earth. Not too warm, not too cold. A gentle balance that allows the body to relax and function normally. Inside the International Space Station, temperature is controlled continuously. Systems regulate heat produced by equipment and human activity. Air circulates slowly, carrying warmth evenly, creating an environment that feels calm and steady, despite the extreme conditions just outside. But even within this controlled space, astronauts remain aware of the environment beyond. During spacewalks, they experience the delicate balance between sunlight and shadow, not through direct sensation on the skin, but through the systems of their suits, which quietly respond to changes in energy, adjusting to maintain comfort. When facing the sun, astronauts know that their suits are reflecting intense radiation, preventing overheating, and when moving into shadow, they trust that insulation and internal systems are retaining warmth. This awareness becomes part of their experience, a calm understanding of how energy flows around them. Interestingly, astronauts often describe temperature in space not as something they feel strongly, but as something managed, something stable, something that fades into the background of their attention, because the systems around them work continuously, preventing extremes from becoming noticeable. However, there are subtle moments where temperature becomes more apparent. Touching surfaces that have been exposed to sunlight or shadow can reveal differences, not instantly dramatic, but noticeable, reminding them of the environment outside the controlled interior. Another quiet aspect of this experience is how the body adapts. Without gravity, without natural convection, heat distribution around the body changes slightly, and airflow systems inside spacecraft help compensate, ensuring that warmth is carried away evenly, maintaining comfort without the need for strong sensations. If you imagine yourself in this environment, floating gently, surrounded by soft mechanical hums, stable air, and controlled warmth, you would not feel the harshness of space, but rather a calm and consistent environment, while knowing that just beyond the walls, the universe remains vast, silent, and deeply cold. This creates a unique perspective where temperature is not something to react to, but something to trust, something maintained quietly by systems working in the background, allowing the mind to relax, to focus, to drift without distraction. As your thoughts settle further, you begin to feel that even in the coldest environment imaginable, comfort can exist, not naturally given, but carefully created, sustained through understanding and gentle control. And in that calm and controlled space, astronauts experience the universe not as a place of harsh extremes, but as a quiet and manageable environment, where temperature is no longer a challenge, but a softly balanced condition that allows them to move, work, and simply exist in peace. As we continue drifting slowly through this vast and silent universe, we now arrive at one of the most fascinating questions. Where are the coldest places that have ever been observed? Not just the average background of space, but specific regions where temperature drops even further, approaching the quiet limit of what is physically possible. Even though most of space already exists at temperatures just a few degrees above absolute zero, there are certain locations where conditions become even more extreme, not through the presence of something actively cooling the environment, but through the absence of energy, the shielding from radiation. and the gentle isolation from external influences. One of the most remarkable examples is found within dense molecular clouds, deep regions of gas and dust where light from nearby stars cannot easily reach. These clouds act like natural shields, blocking radiation and allowing temperatures to fall to incredibly low levels, sometimes as low as a few degrees above absolute zero, creating environments that are colder than most of the surrounding space. In these regions, particles move extremely slowly. Interactions are rare, and energy is minimal. Everything exists in a kind of suspended calm, where change happens over very long time scales, and temperature remains steady, quiet, and deeply low. Another fascinating location is the Boomerang Nebula, often described as one of the coldest known natural places in the universe, where temperatures have been measured even lower than the cosmic background radiation, due to a rapid expansion of gas that causes it to cool dramatically. This creates a rare condition where a specific region becomes colder than the general temperature of space itself. This kind of cooling happens because as gas expands, it loses energy, spreading its particles over a larger volume, reducing their motion and, therefore, lowering temperature. A process that feels almost like a gentle stretching of energy until it becomes quieter and colder. Even closer to Earth, scientists have created laboratory conditions that reach temperatures even closer to absolute zero than most natural environments, using advanced techniques to remove energy from atoms, slowing their motion to an almost complete standstill, showing that while nature reaches incredible limits, controlled experiments can push even further, though only in very small and carefully isolated systems. What is especially calming about these coldest places is how stable they are, not filled with sudden changes or dramatic movement, but existing in a quiet balance, where energy is minimal and everything moves slowly, almost imperceptibly. If you imagine drifting into one of these regions, you would not feel an instant shock of cold, but rather a deep and steady stillness, a place where warmth has long since faded, where motion is reduced to its quietest form, where everything rests in a calm and almost timeless state. These environments remind us that the universe is not only vast, but also capable of reaching incredible extremes, not through chaos, but through quiet processes, through the gentle absence of energy, through isolation and distance. As your thoughts settle into this idea, you begin to feel that even the coldest places are not harsh or hostile, but peaceful, slow, and deeply calm. Places where energy has softened, where motion has quieted, where everything exists in a state of near stillness. And in that stillness, the universe reveals one of its most subtle truths, that extreme cold is not a violent condition, but a gentle absence, a quiet space where energy fades, leaving behind a calm and endless silence that stretches across the cosmos. As we slowly reach the end of this calm and drifting journey, we return to the question that began it all, a question that now feels deeper and softer than before. Is space truly cold, or is it something else entirely? Something more subtle, more quiet, more difficult to describe with simple words. At first, calling space cold seems natural, because when we think of it, we imagine extreme temperatures, numbers close to absolute zero, environments where warmth cannot easily exist, and in many ways this is true. Space does not hold heat. It does not store energy, and objects placed within it will slowly lose their warmth over time. But as we have gently explored, this cold is not like the cold we know on Earth. It is not a force that surrounds you, not something that presses against your skin, not something that rushes in and takes heat away quickly. Instead, it is the absence of everything that would normally carry and share energy. Space does not actively make things cold. It simply allows heat to leave, quietly and continuously, without resistance, without return. Warmth fades not because it is pulled away, but because it is free to travel outward endlessly into the vast distance. This creates a different way of understanding temperature, one that is not based on sensation, but on balance, on the relationship between energy gained and energy lost, on the presence or absence of radiation, on exposure to light, and the quiet influence of the cosmic background. In sunlight, warmth appears, gently building as energy is absorbed. In shadow, warmth fades, slowly drifting away. And in the deepest regions of space, far from any star, temperature settles into a calm and steady baseline, just above absolute zero, not changing rapidly, not fluctuating, but remaining soft and consistent. This means that space is not simply cold, but conditionally warm or cold depending on energy. It is a place where temperature is not fixed, but always in balance, always shaped by what is present and what is absent, by light, by matter, by motion, and by stillness. If you imagine yourself floating in this vast emptiness, you would not feel cold in the way you expect. You would feel the slow loss of warmth, the gentle fading of energy, the quiet transition toward equilibrium, not dramatic, not sudden, but calm and continuous. And as your thoughts settle fully into this idea, the concept of cold begins to change. It becomes less about temperature and more about emptiness, less about freezing and more about silence, less about force and more about absence. Space, in its true nature, is not a freezing void, but a quiet expanse where energy moves freely, where heat is not held, where warmth is not shared, where everything exists in a gentle balance between what is given and what is lost. And in that balance, there is a kind of peace, a stillness that stretches across unimaginable distances, a calm that does not disturb, a silence that does not demand, a cold that is not harsh, but soft and distant. As you slowly drift into rest with this understanding, the universe no longer feels empty in a lonely way, but open in a peaceful way, not cold in a harsh sense, but quiet in a gentle sense, a place where everything slows down, where energy softens, and where warmth, light, and motion all fade gently into the endless and calming dark. As we continue drifting gently beyond the edges of our previous thoughts, we begin to notice something even larger than space itself. Something that unfolds not across distance, but across time. The quiet and continuous cooling of the entire universe. A process so slow that it cannot be felt, only understood, like a deep and steady breath that has been expanding for billions of years. In the earliest moments of the universe, everything was incredibly hot. Energy filled every region. Particles moved rapidly. Light was intense and everywhere. But as the universe expanded, this energy began to spread out, becoming less concentrated, less intense, and gradually cooler, not suddenly, not dramatically, but slowly, gently, over immense stretches of time. This cooling is not caused by something removing heat, but by space itself expanding, stretching the energy within it. As light travels through this expanding space, its wavelength increases, its energy decreases, and with that, the temperature associated with it becomes lower, softer, more quiet. The faint background radiation that fills the universe today, the gentle glow that exists everywhere, is a direct result of this process. Once it was intense and bright, now it is calm and cold, just a few degrees above absolute zero. A quiet reminder of how much the universe has changed over time. And this process is still continuing, even now. The universe is still expanding, still stretching, still cooling. The temperature of the background radiation slowly decreasing, becoming even closer to absolute zero, not in our lifetime, not even over millions of years, but over timescales so vast they are difficult to fully imagine. As galaxies move farther apart, as stars slowly fade and burn out, as energy becomes more and more spread out, the universe gradually becomes a colder place, not through sudden events, but through the quiet passage of time, through the steady expansion that never stops. In the distant future, this process may lead to a universe where most stars have faded, where light is rare, where energy is minimal, and where temperature approaches its lowest possible state almost everywhere. A calm and silent condition, often described as a kind of cosmic stillness. But even then, absolute zero may never be fully reached. There will always be small traces of energy, tiny movements, faint radiation, subtle activity that prevents complete stillness, ensuring that the universe remains gently active, even in its coldest state. If you imagine drifting not just through space, but through time itself, you would notice this gradual change, not something you could see moment by moment, but something that reveals itself over vast periods, a slow fading of warmth, a quiet softening of energy across the entire cosmos. This creates a peaceful and almost meditative image of the universe, not as something rushing toward an end, but as something gently relaxing, slowly cooling, gradually becoming more still, more quiet, more calm. As your thoughts settle into this long and gentle timeline, you begin to feel that cold in the universe is not just about space, but about time, about the gradual spreading of energy, about the quiet transformation of everything into a softer and more peaceful state. And in that slow and endless cooling, the universe continues its silent journey, expanding, softening, and drifting toward a calm that is deeper than anything we can experience, a stillness that stretches not only across space, but across eternity itself. As we continue drifting quietly through this vast and slowly cooling universe, we begin to reach a point where energy itself starts to feel distant, not gone, not absent, but faint, stretched, and gentle, existing in such small amounts that motion becomes soft, interactions become rare, and everything seems to move toward a calm and almost motionless state. In earlier parts of our journey, we explored how temperature is simply the motion of particles, how warmth comes from activity, from movement, from energy being shared and transferred. But here, in these distant and quiet conditions, that motion becomes incredibly slow. Particles drift rather than collide. Energy exists, but barely changes anything around it. This does not mean that everything stops completely, because true stillness, absolute zero, is never fully reached, but it means that change becomes so slow that it feels almost invisible, like a gentle pause that lasts for millions, even billions of years, where nothing rushes, nothing pushes, everything simply exists. Light, which once traveled intensely between stars and galaxies, becomes weaker over time, stretched by the expansion of space, its energy reduced, its presence softened, until it becomes part of a faint background, barely noticeable, yet still present, still moving, still carrying traces of the past. Matter also begins to spread out more. Galaxies drift apart, stars burn through their energy, and fewer new sources of heat are created, leading to a universe where warmth becomes rare, not completely gone, but less common, less concentrated, more distant from any single location. In such a universe, temperature no longer feels like a changing condition, but more like a constant and gentle baseline, always low, always calm, always close to the quiet limit set by the remaining energy in space, not fluctuating dramatically, not rising or falling quickly, but remaining steady over immense stretches of time. If you imagine yourself in this distant future, floating through space where energy is faint and spread thin, you would not feel sudden changes, no sharp differences between warm and cold, only a continuous and soft condition, where warmth has faded into something subtle, something almost unnoticeable. This creates a sense of deep stillness, where time itself feels slower, not because it actually changes, but because so little happens, so little energy moves, so few interactions occur, that everything appears calm, quiet, and gently suspended. Even processes that once seemed powerful, like the formation of stars or the collision of galaxies, become less frequent, less intense, giving way to a universe that is not empty, but peaceful, not inactive, but quiet, where energy continues to exist, but in a softer, more distant form. As your thoughts settle deeper into this idea, you begin to feel that cold in the universe is not just about low temperature, but about the softness of energy, the quietness of motion, the gentle fading of activity across time and space. And in that fading, there is no urgency, no sudden ending, only a slow and continuous transition toward calm, where everything remains, but in a quieter way, a softer way, a way that feels almost like rest, stretched across the infinite darkness of the universe.
you.